This year, we are happy to have our good partner, QuickerSim, to be with us. Later, Mr. Michal is going to share two of their core technologies. Cubot is it's a whole new solution for battery thermal simulation. And it's not just fast, it's ultra fast. And the Piran is a new idea for the battery the degradation prediction. Yeah, okay, so Miho, I think we are ready. Yeah, just get to it. Yeah, thank you.
Okay, hello everyone. So first of all, thank you for having me here in Taiwan. It's my first time here and I love it very much. But let's get to the presentation. So I will be talking about our two tools. The first one is Cubot for battery thermal prediction, and the other one is Piran for the battery degradation prediction. And our company is called QuickerSim, and we like to make things quicker. So let's start with the conclusions, as it's also our last presentation today. So I want to grab your attention by showing you some results. So we have a battery pack here. It's not a very complex one, but also not a very simple one. We have 96 battery cells inside, some connectors, some smaller details. So you can see that the mesh is quite dense here. There are also some other details on the cover so that the battery pack is not too simple. And we have also simulated that battery pack for half an hour of operation. And the current profile that we have used is quite variable, so that we see some more realistic approach here. So we have simulated that battery pack using our tool Cubot on a regular PC with just Intel i7 processor, 24 gigabytes of RAM, and the mesh here was 9 million elements. So you can think how fast this should go. And with Cubot, it took only 100 seconds. So that's the speed, the ultra-fast speed that we offer. But how can you use it? So basically, there are three stages of battery development that we have seen. There are battery cell level, battery pack level, and system or vehicle level teams, usually, in companies. We don't go into the battery cell level details. So let's start with the battery pack. In the battery pack, basically you can simulate with Cubot as in any other CFD tool. You can get your 3D geometry and get your temperatures the same way as you would with ANSYS Fluent or Star CCM+, but you can make it much, much quicker. And then in system or vehicle level, we integrate with MATLAB Simulink. So basically you can export your 3D battery model into a Simulink block and then use it in Simulink as just one of the components. And what's the most important thing here is that even in Simulink, Cubot still solves a 3D problem. So you don't lose any of the data, and it is still, it's not like 0D or 1D simplification. You can get the exact temperature at the point where you would normally have your temperature sensors, for example. And if you want a more accurate electrical model, you can use external battery electrical models. So for example, you can either build your own model using Simulink blocks or Simscape blocks, or you can use external companies' models, for example, like Batimo. And there is also a gap between the battery detailed 3D simulations and Simulink or system level simulations, because there are usually two teams, and the system level team needs to somehow make a 0D or 1D model for the system level simulations. so that it corresponds as much as they can with the detailed 3D model. And usually, some engineer or a couple of engineers would take a couple of weeks or maybe sometimes months to prepare a model which would correspond accurately to the 3D model. But with Cubot, it is much, much easier. So basically, you would do the same things as you would using the in the battery pack level simulation. You would start with the CFD mesh, build the model in Cubot, or if the battery level team would use Cubot, they would have done it already. And then to make a Simulink block out of it, you just generate it. You use one function, and then you have a block which you can import into your Simulink model, and that's it. No work, no extra work needed. But how it works? It is so fast thanks to the reduced order modeling approach that we use. So, like the regular CFD tool, you would first start with the CAD model, then you would have the mesh, and then you would have the results. Of course, normally it will be much more complex than this, but just for the presentation purposes. So what happens underneath is that the CFD solver would need to solve the partial differential equations for the heat transfer. If there is fluid flow, then also Navier-Stokes equations, and it would usually do it either by the finite volume method, like most of the CFD solvers do, or by the finite element method, like most of the structural solvers do. And if we're talking about the finite element method, you need to specify the temperature at each time instance and at each node, and in between you can, for example, use linear shape functions to approximate in between. And as for the heat transfer equation, in the discretized form, we have the term responsible for the mass inertia, the term responsible for the convection and for the conduction, and the heat source, which in battery pack simulations, it's usually just the battery cell which generates heat. And just for the simplicity of my explanation, let's drop the convective term. We do take it into account in Cubot, but just to make it simpler and easier to explain in our limited time, I will not take it into account here. So we are left with a simplified equation just with the mass inertia and with the conduction. And if we take into account the trick from partial differential equations, where we can assume that our function here can be represented as a series of two functions, one dependent on the time and the other on the on space, we can put it back into the original equation, we end up with a generalized eigenvalue problem, which is quite similar to what we usually do with, for example, structural simulations of beams, where we would like to simulate the vibrations of those beams. We also use the eigenmodes. So it's a very similar approach, but for the temperatures. And here you can see some of the exemplary eigenmodes of our solution. These do not exist in physics, but can be represented mathematically and can be used to populate our eigenvalue space, eigenvector space, and used to solve the problem. And what's the advantage of that solution? The advantage of that solution is that it's in the number of equations that we need to solve. In the finite element interpolation, the number of equations is equal to the number of nodes, which in big battery packs goes in millions. While in reduced order model approximation that we use, it is equal to number of eigenmodes, which is much, much lower. If we usually take around 10 to 20 eigenmodes per component, so the number of equations that we need to use in our approximation is lower by a factor of 100, even 1,000, depending on the model. But the most important part probably are the results. So we take a very simple problem for the validation purposes. And we simulate that using Cubot and using a full CFD model. So you can see that there are some slight differences, like for example, this red color here is a bit darker than this red color here. But when we go into the numbers, you can see that the maximum absolute error that we have seen is just below 0.6 degrees Celsius, while the mean absolute error is just above 0.2 degrees Celsius. So taking into account the time difference and the numerical power required for those simulations, this is really a negligible difference, negligible error. So let me go back to the example that I've shown you at the beginning. This time it's the same battery pack, but with a bit smaller mesh. And we have done a couple of tests on that. So first, we tried checking how much the number of modes per component is, how much the time for the model order reduction phase is dependent on the number of modes. Because maybe first let me tell you that there are two stages of the simulation here. Using Cubot, first is the model order reduction, which reduces the model, and then we have the simulation. The model order reduction phase takes the most time in our approach. However, it doesn't need to be done each time we want to simulate. You need to redo the model order reduction only if you change something to the geometry of the battery pack, or you want to add or remove boundary conditions. If you want to simulate your battery pack under different current profile, under different cooling profile, or in different environmental conditions, you don't have to prepare the model order reduction again. So going back here, you can see that the number of modes it has a slight take on the model order reduction time, but it's not very much. Like for example, here on just 5 modes, we have 450 seconds, and then at 50 modes we have 500 seconds. However, when we go to the simulation time, you can see that the simulation time rises drastically with the number of modes. But as I've said earlier, we usually just need about 10 to 20 modes for the simulation to give you good results. Like here we can see that at the beginning, when we have 5 modes, we can see that there are some discrepancies in the temperature, but then from around 10, the temperature is quite steady. So now let's get to the impact of the mesh on our simulations. We have 3 meshes, one coarse, so like 1.9 million elements, then medium 4.7, and very fine of 9 million elements. So you can see the impact of the mesh is not very big here on the results, because we don't solve with the mesh, we solve with the eigenvalue in the eigenvalue space. But the reduction time is much bigger for the higher mesh. However, the simulation time is also quite steady. So what it tells us is that you can have a very fine mesh with a lot of small details in your battery pack, and the simulation will not be much longer than if you would have a very simplified battery pack. So you don't need a lot of simplifications for your simulation to be quick. It will take more time for the reduction phase. However, the simulation phase will be the same whether you have a very detailed battery pack or a simplified one. And for the verification and validation, we have done our verification together with Solaris Bus & Coach. It's a Polish electric bus manufacturer, actually one of the biggest, if not the biggest, electric bus manufacturer in the European Union. So we have cooperated with their engineers for half a year during the early stages of the development of Cubot. And we have validated our results on their battery packs, both in CFD analysis and in laboratory testing. So when we go to the comparison of Cubot against the CFD solvers, we have simulated their battery module with around 100 battery cells inside, both with Cubot and with a CFD solver. So the pre-processing time, so basically the time you need to spend, the engineer needs to spend to make the simulation happen, is also much smaller using Cubot, because Cubot is a tool dedicated for battery packs. So when you get to know how to use it, it's really much easier and much quicker to use than CFD solvers, just because it is dedicated for that purpose. And then when we go to the computation time, 15 minutes of operation of driving profile for that battery pack. In Cubot, on a regular PC, it took 40 minutes for the reduction and 15 minutes for the simulation, while with CFD solver, it was over 48 hours, and not on a regular PC, but on a 100-core HPC. So not only with Cubot we have a faster simulation, we also require less numerical power. And as for the results, you can see there are, again, some slight differences, like the temperatures are a bit higher here than here. However, the maximum error here in the entire battery pack, not in this cross-section, did not exceed 0.8 degrees Celsius. So considering that this was done in 15 minutes on a PC, and this took 2 days on HPC, I guess it's a really small difference for this. And here's the same for the cooling plate in that battery pack. And lastly, about Cubot, we integrate with a couple of tools. So of course we integrate with MATLAB and Simulink and Simscape, like I mentioned. So you can build your electrical models using Simscape or Simulink blocks. We also integrate with Batimo, and you can import the mesh that you can build in other tools, like using the CGNS format, using Nastran format, meshes from StarCCM Plus or from ANSYS, also from ANSA as well. But let's stop here about Cubot, and let's now focus on the second topic, which is the battery degradation prediction. It's our newest development. It's not ready yet. We plan to have it very soon. But let's start with why we would like to predict degradation of the battery cells. The 3 main reasons we have here is battery cell selection, battery pack development, and analysis and optimization during battery life cycle. There are probably many more reasons you can think about, and I would be glad to hear them. But let's focus on those 3 right now. And what are the issues with those problems? In the battery cell selection, there are just a lot of cells, and there are new ones coming all the time, and there is just no time to test them all. And the data sheets that they go with usually have just a very limited information. Like for example, here the only information about the cycle life that we get is that for 0.5 C or 1 C current at 25 degrees Celsius, the cell should have 80% SOH for at least 1,000 cycles. But we know very well that this is not how the battery cell will be used. No driver will use the battery cell constantly at a steady current at 25 degrees Celsius. So basically, you don't know how the battery cell will age. Then the battery pack development, the testing of the entire battery pack is very long and very expensive. So here you need to test a lot of small battery cells. Here you need to test one big battery pack, which is probably even more expensive to test than the couple of battery cells, just because of its size. You need to have the cooling plate, you need to have the entire battery pack basically there to test it. And then in the analysis and optimization during battery life cycle, there is very limited data at the beginning of the life cycle of your battery pack. So basically, for the first couple of months or a year or 2, you don't have the data to compare to, you don't have the data to extrapolate from. And we want to solve all of those issues with our tool Piran. So how it would work is that you just need a very limited number of tests, just 100 or 200 cycles of a single battery cell. And then based on that, we use our automatic cell identification, which based on those short tests identifies electrochemical models. 3 electrochemical models, each more complex than the previous one. So first we do the single particle model, then the single particle model with electrolyte, and at last the most advanced model, the P2D model. And then using those models and combining them with 3 degradation models, so loss of active material, SEI growth, and loss of lithium inventory through growth and cracking, we can simulate how the battery cell will degrade. And what's unique about this feature, about this tool, is that we don't need the extensive testing. We just need 100 or 200 cycles. We don't need any previous data because it's a physics-based model. It's not data-based, it's not statistics. It's just physics, and thanks to that, you don't need to have a big data analysis from a couple of months or a couple of years of driving of entire fleet to have something to compare to. And what's more, we plan to have Piran integrated with Cubot so that you can have both of those tools even more accurate. So first of all, with Cubot, you can simulate the thermal conditions of your battery pack based on the cell data that you have from the initial battery cell. Then, using Cubot, you can import that thermal profile into Piran. And then in Piran, you can simulate how the battery will degrade for a couple of 100 cycles, for example, depending on how often you want to update it. And then you can update the equivalent circuit model of the battery cell to Cubot, so that Cubot has an updated, the aged battery cell to simulate with. And then based on that new model, Cubot will simulate again the thermal profile and put it back into Piran. And then Piran will simulate with the updated profile and the cycle will complete as many times as you want it to. And when we plan to have it? Now, so in Q2 and Q3 of this year, we are still in the development phases and validation phases based on the laboratory testing that we do. We are doing the customer interviews and UA and UX mockups. So if you are interested in a tool like this, I am more than happy to discuss this with you. Then further in the year, we plan to have a working MVP and show this MVP to potential customers to get some initial feedback so that we can make this tool even more appealing. And then the full product release will be made at the end of the year. So as I'm here, I would like to ask you for some help if you are willing to. So first of all, if you're interested in the battery thermal simulations and making them really quickly, I would be very happy to discuss this topic with battery simulation departments, give you Cubot for some trial periods, or do POC projects to show you what actual results you can get from that. If you're interested in the battery degradation topics, I would gladly do the same. I would gladly discuss it with you and get to know how you would like to use a tool like this, for what it might be interesting for you, and what features you might want to see in that. Also, we like to cooperate with universities and educational staff. So we already cooperate with a couple of universities and a couple of student teams. So we are more than happy to broaden those contacts. And also any other business partnerships that may come into your mind, I would be glad to discuss them. And just at the end, briefly about QuickerSim. We're a small team of 20 people. We are based in Poland. We're founded by two PhDs during their PhD in computational fluid dynamics. And we have around 10 years of numerical models development, 5 years of QuickerSim operation. And if you would like to contact us, here's me. I'm the product manager for e-mobility. Here's my email. Here is also our CEO and CTO. But if you want to send emails, it's probably best to send it to me, as I will make sure to answer you as quickly as possible. Okay. So thank you. And are there any questions?
Thank you for your presentation. I'm interested in Piran. So could you please go back to the first slide of the Piran? Oh yeah, this slide. Okay. Our company have the production line for the lithium-ion battery, and we do a lot of the QA testing for the lithium-ion battery, and record a lot of data for the lab prediction over the year and the years. So here you just mentioned the short test. That means that only 100 to 200 cycles can do the prediction. So that is an amazing number compared with us, what we are doing right now, because we are doing over and over years and years. So what is the basic concept you can implement by your idea?
So basically, I can't tell you how exactly it's done because I'm not a technical person responsible for this. If you would like to know it in much detail, I would gladly discuss this with you during an online call with our technical team. However, I can tell you that after initial validation that we have done, we have already a working example of a battery cell where we, after I think 200 something cycles, we have a working example of the automatic cell identification of all of those models. I'm not sure if we have already something to compare about the battery degradation from a for longer cycles, but definitely our team from the technical department will be happy to discuss.
Okay, good. So, so please let me know your name, business card.
I will give it to you.
Okay, because as you know, we are doing the energy storage system, the large scale, the megawatt. So a lot of battery pack inside the battery cabinet.
Yeah.
And one 40 feet container, including 10,000 of the battery cells. So the reliability and the life cycle prediction is the big challenge for us. How to provide a more accurate number to our customer to demonstrate our reliability and the ROI, return of inventory.
I understand.
So, yeah, that is the key. Okay, thanks.
Okay, thank you.
One more question regarding your Cubot.
Yes.
So you use the reduced order model to speed up your simulation, reduce the simulation time. So the reduced order, I think we can do the same thing by using the third-party simulation tool. For example, the Frozen. We use the reduced mesh. We can do the same thing. So what is the key feature and compare with your competitor?
For your solution that you mentioned, do you need any previous simulations for the?
Yes, you use the reduced order to speed up your simulation, but we use the the less number of the mesh for the structure.
Yes,
to
but
speed up.
if you use the less dense mesh,
Yes.
then you lose the accuracy and a lot of it if you make the mesh a lot more coarse.
Yeah, hold second. So from understanding, we can use the less mesh to do hold second. We use the less mesh to do the roughly simulation and to predict which portion is the hotspot area. And then we increase the mesh as the critical portion, critical area, re-simulate again to get a more accurate number of the thermal information.
Well, you can do it that way. However, it still will not be as fast. And then even using a coarse mesh for steady-state simulations, coarse mesh will do just fine. However, in battery packs, you mostly want to simulate transient meshes because battery packs mostly operate on transient, on variable current profiles. So then, even then, when you want to have a time step, for example, of 1 second or of 10 seconds, then if you want to simulate a long driving profile or a long current profile, then the coarse mesh will still be very long.
Okay,
and with Cubot, we can make it much, much faster.
Yeah, sure. Yeah, I fully agree with you because you mentioned the transient response of the battery. Yes. We always keep the steady state for the simulation.
For steady state, coarse mesh is just fine. But if you want to make a transient case, then, for example, I can tell you, we did one of the customer projects that we did was for a company which makes battery packs for motorcycles. So they wanted to simulate that. They simulated that with a different company which used ANSYS Fluent. For the simulations. So to simulate a battery pack with 200 battery cells inside for just 1 minute, they had to first simulate a couple of battery cells, then out of that make a simplified model of the smaller module, and then based on that make a simplified model of the entire battery pack. And those are 3 stages of simplifications of simulations, and still the results were not very accurate because of the simplifications. And it took still a lot of time just to simulate 1 or 2 minutes. And then in Cubot, we just took the entire battery pack and simulated it for a current profile of 2 hours. And it worked just fine.
Okay, I see. Okay, so please let me know your message, communication message. And I can bridge you and our battery team.
Okay, thank you.
You're welcome.
大家也可以问中文，我们可以协助大家跟讲员简单的沟通。OK。
So you mentioned that you have some collaboration experiences with EV bus. So I'm curious about that. Does the testing flow or validation flow in your software based on or follow any electrical vehicle standards?
Are you asking if we can simulate for some certifications, right?
Yes.
So basically, it would depend on what certification. Just basic thermal simulations or simulations including everything before the thermal runaway, then we can do it. But if you want to see what happens during the thermal runaway, so the electrochemical stuff, or for example, puncturing of the battery cell, then we cannot do that because we just don't go into the electrochemistry of the battery cell in Cubot. So to answer your question, if it's related just to the thermal side, then yes. If it's something related to the destruction of the battery cell, then rather not.
Okay, thank you.